Today, my partner and I will be talking about GPS, also known as the Global Positioning System. So, what is GPS exactly, and how does it work? A point is found by knowing the distance between 3 or 4 other points. This can be measured by determining the time it takes for a radio signal to go from one point to another. Basic GPS can provide 7-meter accuracy for 95% of the time. GPS satellites carry atomic clocks that provide very exact times, allowing for the high accuracy of the GPS system. The following process is how an object or location is found with satellites. First, we impose X, Y, and Z coordinates on our circle. So, the unit circle we have on the right becomes a unit sphere, which can be seen on the left. As suggested by one of our sources, we established that the Earth radius is 1 unit, therefore giving us x squared plus y squared plus z squared is equal to 1. Here, c is the speed of light in units of Earth radii per hundredths of a second. This is what we will be using when computing distance. Here is our example satellite data. Our goal in the following slides is to calculate the values of x, y, z, and t.
Here is our example satellite data. We can see that it has 3 columns and 5 rows. The first column has the data about which satellite we are talking about. The second one, the position, and the third, the time. Satellite 1 is at position X 1.11, Y 1.55, and Z minus 0.54. Satellite 2 is at position X 227, Y 0.51, and Z 0.42. Satellite 3 is at position X0, Y 158, and Z 0.21. And satellite 4 is at position X 151, Y 1.01, and Z minus 0.23. Our goal in the following slides is to calculate the values of x, y, z, and t. Now we're going to be computing distance from satellite 1. Distance is equal to velocity multiplied by time. Another way of finding distance is to apply the formula, the square root of x minus x1 squared plus y minus y1 squared plus z minus z1 squared. Now, by equating these two formulas, we're able to create an equation for each satellite, therefore giving us a system of equations that we must solve. This will give us as equation 1, x squared minus 2.22x plus y squared minus 3.10y plus z squared plus 1.08z plus 3.93 is equal to 0.22 t squared minus 7.15 to the times 10 to the 8th power plus 5.78 times 10 to the 17th power. Now we're going to be repeating the same process but with the distance from satellite 2, satellite 3, and satellite 4. For this, we're going to be left with equation 2 be x squared minus 4.54 x plus y squared minus 1.02y plus z squared plus 0.89 z plus 5.59 it's equal to 0.22 t squared minus 7.15 times 10 to the 8th power t plus 5.78 times 10 to the 17th power. As equation 3, x squared plus y squared minus 3.16y plus z squared minus 0.43z plus 2.55 it's equal to 0.22 t squared minus 7.15 times 10 to the 8th power t plus 5.78 times 10 to the 17th power. And the last equation will be equation 4. That will be x squared minus 3.03x plus y squared minus 2.02y plus z squared plus 0.96z plus 3.37 is equal to 0.22 t squared minus 7.15 times 10 to the 8th power t plus 5.78 times 10 to the 17th power. And with these four formulas, we're going to be able to find the location. This is the way the augmented matrix ends up being, and through some calculus and some procedures of Gauss-Jordan, we end up having the last reduced augmented matrix, and we end up with three equations: x equal to minus 1.8 times 10 to the 8th power plus 0.9 t, y equal minus 4.3 times 10 to the 8th power plus 0.25 t, and z equal to 0.48 times 10 to the 9th power plus 0.16 t. Now, substituting our answers back into the formula, bt is equal to square root of x minus x1 squared plus y minus y1 squared plus z minus z1 squared, we obtain values for t1 and t2, and x, y, and z in terms of t. Those, we put them together, and after analyzing the data, t1 ends up being out of range, while t2 is right in the range. So those are the coordinates that we were trying to calculate with the GPS.
Now we have another example that is very similar to our first one. Here we can see our two distance formulas and the resulting formula that we get by combining the two. We repeat this process for satellite 2, 3, and 4. Now, subtracting our equation number 1 from 2, 3, and 4, we now have 3 different equations. In the next 4 slides, you can see how we reduce this augmented matrix. Our resulting values are x is equal to 3.29 plus 1.112 t, y is equal to 3.41 plus 1.517 t, z is equal to 0.698 minus 0.117 t. Now we replace x, y, and z into our equation number 1. Using the quadratic formula, we get the results for T1 and T2. Using those values of T1 and T2, we input them back into our equations that equal x, y, and z, which gives us our final coordinates for T1 and T2.